All right, we're going to start taking a look at infinite sequences in series. We're going to have to do this over a couple parts. Today we're going to just start talking about what does that even mean and what do they look like and what's the notation I can use and start looking for some patterns. So infinite, first of all, means doesn't stop, obviously. And sequences, we're talking about those lists of numbers. So we have some ordered specific set of numbers. There's a rule that we get from one to the next. So like arithmetic, for example, we talked about those already. Common difference to move from one to the next. Geometric, there's a common ratio. We're multiplying by something. Today we're going to branch out a little bit more, though. We're not just going to talk about arithmetic and geometric. We're going to talk about other types of ways to generate the sequences, the list of numbers. The rules don't always have to be add something or times by something. So the rules can be a lot more involved than that. So I'm going to start with one that is new to us, something that we haven't looked at before. So kind of listing out what these would look like. So here's your term 1, term 2, term 3, term 4, and term 5. So I'm giving you a list, a sequence that has 5 terms. And I bet you could probably predict what the next term would be. Would be 1/6, and then 1/7, and then so on. So I want you to see if you can figure out what the rule would look like. It's definitely not arithmetic. There's not a common difference. There's not a common ratio. We're not multiplying by the same thing. So what does this look like it's doing? Well, if this is term 1 and term 2 and term 3, 4, 5, it looks like every single time we have 1 on top, and it's always just the term number on the bottom. And what variable do we use to stand for term number? Well, that's our n. So it would just be 1 over n. So if I'm going to try to generate a term in this sequence, I just need 1 divided by the term number. So if I want a 100, it would be 1 over 100. If I want a 1,000, it would be 1 over 1,000. So I can get that and generate those terms. Now what I want you to look at is what happens to this term as n gets really, really big, so as it approaches infinity. So this would be the equivalent of what we did earlier in the year of like n behavior, looking for those horizontal asymptotes is another thing that we talked about when we did this. I want you to think about what that would look like for this particular graph. So I want you to go ahead and graph, go to your y equals, and go ahead and graph 1 over x. I want you to see what that looks like. We're going to be doing a lot of the graphs first, and I'm going to do a zoom 6, so we have the whole thing first, so this whole 1 over x graph, which should look familiar. It's one of our parent graphs. Has some symmetries. It has y equals x symmetry, so it has this one. It has y equals negative x symmetry, and it also has origin symmetry, so it's all of those from before. Now, what we talked about earlier, though, is that when you're talking about term numbers, they can never be negative. We don't have a negative term value. So we start with n equals 1, n equals 2, n equals 3. So I'm going to adjust my window here so I'm only seeing starting at 0 for x. That way we can really focus our attention on the picture that we need to. So I want you to think about what happens as the value of the term n gets bigger and bigger and bigger. So what happens as n increases? So I'm just going to make a super rough sketch on this. So what's happening as we go this direction on the graph? Well, it sure looks like the values are approaching down here. So it looks like it's approaching 0. If I go to my table, so I want you to go back to your graphing calculator here, I have my table set at 100 just so I can see some bigger values, but it sure looks like this thing is getting smaller and smaller. If you go out to like a 1,000, a 2,000, a 3,000, it's going to get closer and closer to 0. At some point, your calculator will actually probably say 0, and that's because it just can't handle the rounding. So it's going to at some point not be able to handle that. But this idea of what is it approaching, that's the n behavior that we did earlier. That's this concept that we're going to call a limit. So we're going to talk about these ideas as limits. So what is it getting close to? So what you're going to see for notation is this statement down at the bottom here, LIM. That's short for limit, which is the same thing as asking the question, what happens as n approaches? Now, in this case, it's approaching infinity. You don't have to have infinite limits, so we can have things that approach particular values. We'll see things next in other sections where it could approach, like, say, a number like 5 or 7 or -2. We can talk about limits in many different ways, but we're talking about infinite limits today at the end of the graph, the n behavior. So what we're going to look for is what happens, this is the statement that we'd say, LIM, short for limit, as n approaches infinity of, and then whatever the rule is for the nth term. So we're going to put in 1 over n. So this is the an or the nth term, however you want to say that. That's the rule or the statement that generates the terms in that sequence. And what is that equal to is the value that this term is going to approach, or these terms are going to approach as the n gets larger and larger. So at A100, A200, A2 million, A50 million, what's going to happen? Well, these are all getting closer and closer to 0. When I say that the limit equals 0, we're not saying that the terms actually equal 0. What we're saying is the value of the terms get closer and closer to that amount, but they don't necessarily equal that amount, but it's the value that they're getting close to. So when we ask for a limit, we're really, an infinite limit anyway, we're really asking for that end behavior. So in this case, there would be a horizontal asymptote on this graph at 0. That's the same thing as saying the limit as n approaches infinity of 1 over n is equal to 0. So this is a great example of a graph that we're going to be comparing a lot of things to. What happens to 1 over n is that decreasing sequence that's going to give us a limit of 0. Let's go back and do a limit for something that we're familiar with, though, so we can kind of compare that to things we already know, and those are the kinds of limit statements we're going to be doing today. So I want you to take a look at this sequence of numbers. So I have 7, 7 fourths, 7 sixteenths, and so on. This sequence is actually geometric, so we've talked about ones like this before. And it's geometric with a ratio of 1/4. So those values, those terms, are getting smaller. It's decreasing. So A1, A2, A3, A4, A5, these terms are getting smaller and smaller. So if you remember the AN formula that we did before for geometric, it's A1 r to the n minus 1. So their 7 is our A1, 1/4 is our ratio to the n minus 1. So you could generate any term in the sequence. So we've already talked about this. So if I ask you to do A10, I can plug in and I can do 10 minus 1. For my power, I could do A50. I just kind of want you to get a gut feel of what's happening for these terms. As I get larger and larger values of n, what's going on? What is this doing? So if you can pause the video for a second, go ahead and type those into your calculator. I'd like you to see what numbers you're actually getting here when you do that. So for A10, it's already to the -5th power. For A50, we're at the -29th, and by A100, already at -59th power. These are tiny, but it definitely looks like it's getting closer and closer to 0 for sure. So let's talk about what the limit statement, like how would we write that? So the limit as n approaches infinity, so we're talking about infinite limits, n behavior, of, and remember what comes next, this is our nth term, this is our AN formula, that's the rule, that's how we generate the terms in this sequence. The limit is asking us for what are the terms getting closer to, so we look at those values, like what are these answers getting closer and closer to? Well, 0 for sure. The reason we know that is because it's geometric with a ratio that's less than 1. Because this is less than 1, I know it's going to decay and it's going to go towards 0. Now, if this ratio were greater than 1, if you remember Mean Girls, the limit does not exist. The ratio, if it's bigger than 1, those terms are going to get larger. They're going to grow. It is not going to give you a limit that we can talk about a value for. Those numbers will get infinitely big. So geometric are things we kind of know about. If the ratio is less than 1, it's decay. That means the limit as n approaches infinity is going to equal 0. If the geometric ratio is greater than 1, then we're looking at growth. We know that. We know what those do. And that means the limit as n approaches infinity does not exist. It's going to continue to get bigger and bigger. The values of the function are never going to approach anything. For does not exist, we're going to use the abbreviation DNE, so you'll see that quite a bit over the course of the next few ideas here. So we have to look at what that base is doing. So for geometric, we have a pretty good handle on what's happening. Arithmetic works kind of the same way as geometric with the ratio bigger than 1. Arithmetics either continue to grow or decay. They're linear, right? They never approach any particular value. They're always growing or they're always decaying. They never really level out and approach anything. They don't have horizontal asymptotes. All right, let's talk about other types of graphs then. So I want to get back to that 1 over n idea. So we have this idea of what we call rational functions, ratios that are polynomials we did earlier in the year. When you look at rational functions, things like these, we can look at the limit. We can see if it exists or not by looking at the values in the equation. So being able to show what's happening in those different functions. So what I'd like you to do for this is think about what this itself would generate in terms of terms. So if I had this as my expression, it's not geometric or arithmetic for sure, it's two polynomials in a fraction, what would it be? So how would I find a1, a2, a3? This is supposed to generate a list of values. This is my nth term. Well, how would you find a1? Well, you'd put 1 in for the n's and you'd simplify it. How would you find a2? Put in 2 for n. a3, put in 3 for n. Well, instead of doing that arithmetic myself, I'm going to go ahead and have you graph it on your calculator. And so we can use our table. Don't forget to use parentheses if you're going to type this in, so you get actually dividing what you think you're dividing. That's really important. But let's see what the graph looks like so we can generate those terms and we don't have to do the arithmetic ourselves. Understanding that that's how you'd find those terms, though, is you would just substitute in 1 for a1, 2 for a2, and so on. So I'm going to take a peek at my graph, and I only have it on from 0, greater than 0, because again, we can't have negative values or even decimal values for our term numbers. So we're really just looking at the integer values of this equation, this graph. Should look something like that, though. So if you go into your table set, I'm going to start at 0 so I can grab some of those first terms. I'm going to see that a1, if I plug in a 1, looks like my output was negative 10. So my first term in this sequence is negative 10. And then if I go to my second term, so look at a2, so we're looking at these integer values, negative 2.063. And then the third term in my sequence looks like it's negative 0.3889, and so on. You can actually generate the terms in the sequence. Now, they're not beautiful to look at, but we can certainly do it. Now, what I want to ask you is, what if you did like a million, a 10 million, a 80 million? As these values get huge, what would the limit be, if anything? Is this going to approach anything? Is there a value that we can put in here? All right, so I'm going to do the algebraic method for this first, and then we're going to, or in a second, but first I want you to take a look at the graph and see if you can come up with anything. So if you look at the picture, it kind of looks like this graph is leveling out. It sort of looks like it's flattening out. So what I want you to see if you can figure out is, what does it look like it's flattening out to? I'm going to go to my table set and go to 100. And go back to my table. A100 is already at 1.47. Looks like it's about there. If I do let's say 1,000, go back to my table. 1.497. Gosh, it looks like it's getting pretty darn close to 1.5. So I want to see if that pans out, because I've gone up pretty big already. And I know I haven't done 10 million or anything like that, but I can probably get it to actually say 1.5 if I go to a large enough value for my table set. If I put in, say, let's try 3,000 just to be crazy here, see if it'll take it. Can it handle it? Oh, we're getting super close, so we need to even go even larger, but it sure looks like it's going to 1.5. So let's see algebraically if we can prove why that's happening. So I'm just going to go ahead and do the operation that it said there. If you have a monomial on the bottom, just a single term, you can actually go through and just do the arithmetic. So I'm going to divide every term in the numerator by the denominator and reduce those fractions. Now, I know a lot of you can do that work in your head, and please do, but I want to make sure you see what I'm coming from here. So I'm going to reduce each of those. That would be 3/2. That would be 11 over 4n. This would be 35 over 4n squared. So all I did really is just divide and simplify that fraction. Now, let's take a look at this slide previous. Basically, what this slide is all about is theorems for limits, things you can do with limits. So if you have limits that are added or subtracted, we'll take a look at the top one here, you can separate out those two addition things, or however many they are, and look at the limits of them separately and then add together. Same thing for subtraction. You can separate it out into separate limits and subtract them. If it's a product, you can multiply them separately. If it's division, you can divide them separately. So you really can just break these apart and look at each piece separately to see what happens to each and then put them together. So let's do that, and then we'll talk about that bottom one here. So I'm going to write this as the limit of each of these separately. So the limit as n approaches infinity of the first one, which is 3/2, minus the limit as n approaches infinity of 11 over 4n, minus the limit as n approaches infinity of 35 over 4n squared. And I'm going to look at what happens to each one of these pieces separately. So let's talk about the first one. The limit as n approaches infinity of 3/2. 3/2 is a constant. It's just a number. What happens to 3/2 as n gets big? Well, absolutely nothing, because there's no n with it. It doesn't change. It's a constant. There's no variable there. If you graph y equals 3/2, it's a horizontal line at 1.5. It's not doing anything. It's not changing at all. If you go back to our table here to show this, limit of a constant is equal to the constant because the constant doesn't change. That's why they call them constants. So when I look at that limit then, of that first term, this is just 3/2 minus, okay, let's look at the middle one, 11 over 4n. Now you can graph that on your calculator. Sometimes it's helpful for people to look at it separately. 11 over 4n, what's going to happen as n gets really, really big? Well, you could put in n equals 100. That would be 11 over 400. N equals 1,000. That would be 11 over 4,000. Well, what are they doing? Well, they're getting smaller, of course. The 11 and the 4 don't really matter a whole lot. They're coefficients, but the bottom line is if your denominator gets bigger, the fraction is going to approach 0. It's going to happen every single time, no matter what those numerical things might be. That's going to go to 0. Okay, well, how about 35 over 4n squared then? Well, if 1 over n goes to 0, 1 over n squared is going to go to 0 even faster. That's going to get huge even faster because n equals 100 is not just going to be 100 on the bottom, it's going to be 100 squared. That's big. 1,000 is going to be 1,000 squared. That's even bigger. So when the denominator gets huge, that fraction is going to go to 0. So when I do my arithmetic, then I can just add up my values, or subtract in this case, and it sure looks like my limit is going to equal 3/2. Now again, remember that means it's the value that the terms are getting close to is 3/2. That's what limit means in this situation. We're not saying it actually equals it, like the terms will actually be 3/2. So now I want you to go back and take a look at some of the things we can notice from this. If you look at the highest degree term in the top and the bottom, they both happen to be squared, which is really important. The degrees are equal in this case. The only terms that really matter in calculating your limit are those highest degree terms. If you look at the other two terms, they're not contributing anything to that. The 11n and the 35, those terms are going to 0 as n gets really, really big. So those highest degree terms really rule and determine what's going to happen to our limit. And because they were equal, they have equal weight in that determination. So the 6n squared and the 4n squared, when we reduce that, we just get down to our 3/2. Those are the terms that really matter. Okay, let's take a look at the bottom one. Very similar scenario. See how we have the monomial on the bottom? Again, this is not arithmetic or geometric. These are rational functions, so it's a ratio of two polynomials. What I'm going to do is go ahead and write this out as each of them being divided by the denominator. So we can look at the ratios. We can look and see what's happening at each term separately. So this is kind of the arithmetic that I would do each time. Again, I know you probably don't need to write that first step in green. I would just go ahead and, if I were you, and just do the division in your head and just write what that's equal to. It saves you a little bit of time. All right, so what we can do then is we can take a look at each of these limits separately. So I can look at the limit as n approaches infinity of 1 over n, and I can look at the limit as n approaches infinity of 5/2, and then I can look at the limit as n approaches infinity of 2n. Now I want you to think about what happens to each of these, kind of in conjunction with what the graph looks like. So I'm going to go ahead and have you pause the video, go ahead and type in your equation here so you can have something to look at. I want you to see, don't forget parentheses again, what this graph tells us in terms of n behavior, or the limit as n approaches infinity. So I'm going to go ahead and get this typed in so we can look at this. I'm going to go back to my window being a zoom 6 so we can look at the whole thing. So you can just get an appreciation of what the original picture was. Okay, so it looks like we have two asymptotes on this graph. We have a vertical asymptote on the y-axis at x equals 0, because we definitely can't divide by 0. So we have a vertical asymptote. Can't divide by 0 because of the denominator. But we have another kind in this one. It's not horizontal, actually. There's no horizontal asymptote at all in this graph, which is going to tell us something unique about it. It's actually one of these slant asymptotes. It's a slanted line. And if you recall from the beginning of the year, we talked about this. Slant asymptotes always happen when the degree in the top is exactly 1 greater than the degree in the bottom. So we definitely have a slant asymptote here. But what I need you to focus your attention on is not the entire graph. I'm going to go back to my window again and start it at 0. I want you to focus on just what happens as n, or x, gets really, really big. What's happening to this graph as it keeps going? Well, it's growing, right? It's getting bigger and bigger. If you look in your table, so take a peek in your table once. I'm at 3,000. It looks like it's these are all scientific notation, I believe, too, right? Oh, no, this is just actual values. So it's already at 6,000. I'm at 3,000. So it's growing. Not super fast, but it's definitely growing. It's getting a little bit bigger each time. Now, what does that tell me? If it keeps growing, keeps growing, keeps growing, keeps growing. Let's think about that as we do the limit. So what happens to the limit of 1 over n as n approaches infinity? Well, that's going to go to 0 because the denominator is growing. What happens to 5 halves? Well, it's a constant. Absolutely nothing. It's going to stay 5 halves. Here's the problem. What happens to 2n as n gets really, really big? It's going to grow. It's going to get bigger and bigger. That's linear, right? It doesn't grow very fast, but it gets infinitely large. And here's our problem. We can't do order of operations with infinity. This limit does not exist. If any part of your limit doesn't exist, that means the entire limit does not exist. So here's where we'd be saying our DNE. The reason I can tell that from the graph is because it is growing as I look at those different values. The value of the graph is increasing. How can I tell it from the original equation? Well, look at your highest degree terms. I have a 4n squared in the top, and I've got 2n in the bottom. The degree is bigger on the top than it is in the bottom. Whenever that happens, that's going to be growth. That's really like a degree 1. That's a 2n. So when I look at what that's doing, what happens to 2n, it's going to grow. It's not going to have a limit. So not every infinite limit is going to exist. There's going to be a lot of these where those degrees are higher on top. Those are the ones that really matter. That's going to determine what happens in those equations. All right, so I'm going to go ahead to these two so we can talk through a couple more of these. I want to look at the relationship for the similar kinds of situations and see if you can start seeing what happens with these monomials. So I'm going to try to do these without graphing them first and just go ahead and take a look because I have a monomial in the bottom and just do that reducing, actually do the operation so I can see what's happening. And then again, if you can do that reducing all in one step so you don't have to write it out separately, that's great. If you do have to write it out, then go for it. And then let's see what we get. So the limit as n approaches infinity of 1 over 3n minus the limit as n approaches infinity of 1 over 3. All right, so we're going to take a look and see what happens to each of these separately. So what happens to 1 over 3n? Well, that would go to 0 because if you have an n on the bottom, as n gets bigger, 1 over that larger value is going to get smaller and smaller and smaller. Okay, what happens to a third? Well, absolutely nothing. It's a constant. So 0 minus a third would be negative 1/3. Now, if you graph this, the graph should look like it's going towards negative 1/3. Let's see where you can see that from the original. If I look at the highest degree terms in the top and the bottom, if you notice the degrees are equal here. So we have degree 1 in the top, degree 1 in the bottom. The other terms don't matter then. The smaller degree terms do not contribute as much to what's happening here. It's the highest degree terms that do. Just look at that ratio. Negative 2n divided by 6n, that's your negative 1/3. So for polynomials, you can start looking for some of those patterns. It really helps. But we have an algebraic backup plan that we can show and prove that. All right, let's take a look at number 2. There's something a little bit different about this. This first part looks exactly like the other ones I've been doing, but then we have this plus 3. That just means we're taking the whole graph and shifting it up 3. So you can do operations with limits like this. I can figure out a limit and then I can do numerical things with it like add 3. So let's just see if we can figure out what's inside my red circle here. Let's do this limit. So again, it's a monomial in the bottom, so I can go ahead and take every term in the top and divide it by the term in the bottom, and I can calculate that limit, and then don't forget that there's just going to be this plus 3 on the end. All right, so I'm going to go ahead and reduce, which I know a lot of you can do all at once. You don't have to write it separately. And we want to take a look and see what happens as these terms, the ends get really big, really big. So what happens to the value of that sequence term? So if we write them separately, and I know some of you will be able to kind of get to the point where you don't even need to write what I'm writing in blue. You'll just be able to look at it and say what's happening. But I just want to make sure you understand what we're doing here. We're taking the limit of each of those sentences separately, and don't forget again, there's a plus 3 on the end, and see what happens. So what's the limit as n approaches infinity of 6? Well, 6, it's a constant. What's the limit as n approaches infinity of 2 over n? As n gets big, 2 divided by n would get tiny. And then what happens to 8 over n squared? It gets tiny even faster, and we have our plus 3. So all together, our value of that expression would be 9. The limit was 6, and then we add 3 to it. Now I'm going to encourage you to go back to the original here again and look what's happening. We have a highest degree term in the top and the bottom that are both squared. That means, again, the degrees are equal, so those highest degree terms are the ones that matter. So if we can tell where our degrees are, if it's bigger on top, bigger in the bottom, are they equal, it tells us everything we need to know about what that value would be. So when the degrees are equal, they have equal input as to what that's going to be. All right, so let's take a look back at one last one here, and we'll see how much further we can get. I think we'll finish up with this one. So how is this one different? Well, in the bottom, there's two terms. It's a binomial, so I can't just divide super easily, but what I can do, is I can get ratios in a little bit different way. So what we do is we divide, kind of like what we did for end behavior, every single term in this expression by the highest degree term that we have all together. So by the highest degree term. Whether that highest degree term happens in the numerator or the denominator, doesn't matter. We're going to divide by the highest. So my highest degree term in each of these happen to be n squared. So in my case, I'm going to divide everything by n squared. We're going to graph this one too. So if you want to pause the video and get it typed in there so you can see, that would be great. But all I'm going to do, and again, hopefully you're going to be able to shortcut this and just kind of simplify as you go, but I'm going to take every single term and divide it by n squared. So every single one, because n squared was the highest degree term that I have. And then I'm going to go ahead and reduce that. So we have the limit as n approaches infinity of 5 plus 1 over n plus 4 over n squared. And then we have 1 plus 1 over n squared. And then I can take the limit of each of these separately. So the limit of each of the terms in the numerator and each of the terms in the denominator. So I'm going to see if I can go ahead and just do this and see if that works for everybody so I don't have to write them separately. So what happens is n approaches infinity for 5. Well, nothing. It's a constant. What happens to 1 over n? It would go to 0. What happens to 4 over n squared? Goes to 0, but even faster. What happens to 1? Well, it would stay 1. It's a constant. And 1 over n squared would go to 0, so our limit should be 5. And if you look at the equation on your calculator, if you graph it, you should be seeing exactly the same thing. So if I graph my statement and want to see what that looks like, it should give me the same sort of idea. So if you go back again and think about what my highest degree term was in the top and the bottom, the only terms that really matter are that highest degree term. And because they were the same degree, they were n squared for both of them, what that's telling me is that they're growing at the same rate, and they will have equal input as to what happens, oh darn, on that expression. So when we look at actually solving, we would have equal input. They're both going to determine what's going to happen, as opposed to having, like, say, a bigger degree on top, that would be more influential, or a bigger degree on the bottom, that would be more influential, but these are equal. So if we look at that graph, sure looks like it's leveling out at 5. We can go to our table and we can see that as well. It gets super, super close to that. All right, so if it's a binomial on the bottom, then we have a little bit different strategy as to how we're going to write that out into that. All right, so that's going to be the end of the part 1. I'll do some more examples in the next probably 1 or 2 parts.